Time travel. The very phrase sparks our imagination. It takes us on journeys to distant pasts and unknown futures. We've all dreamed of witnessing historical events, righting past wrongs, or glimpsing our future selves. For centuries, time travel has been a staple of science fiction, captivating audiences with its boundless possibilities. But what if time travel is more than just a fantastical idea? What if it's grounded in scientific principles? While we haven't quite built a time machine yet, theoretical physics suggests that time travel might actually be possible. The journey begins with Albert Einstein, whose groundbreaking theories of relativity revolutionized our understanding of time and space. Einstein's work laid the foundation for the concept of time as a flexible entity, not the rigid, unchanging constant we perceive it to be. Einstein's theories opened up a Pandora's box of possibilities, suggesting that time travel might not be just a flight of fancy. It could be a real possibility, waiting to be unlocked by scientific exploration and discovery. The journey into the science of time travel is a thrilling one, full of mind-bending concepts and intriguing possibilities. So buckle up as we embark on this exploration of time travel, where science fiction meets scientific possibility. Before Einstein, time was considered an absolute, ticking away at the same rate for everyone. But Einstein proposed that time is relative.
Time can pass at different rates for observers in motion or different gravitational fields. This is known as time dilation, a key prediction of Einstein's special relativity. Time slows down for objects in motion. The faster an object moves, the slower time passes for it. This effect is more pronounced as an object approaches the speed of light.
Imagine two synchronized clocks, one on Earth and the other on a spaceship traveling at high speeds. When the spaceship returns, the onboard clock shows less time has passed. Einstein's theories transform time into a flexible dimension intertwined with space. To grasp the concept of time travel, we need to understand how time and space are interconnected, forming a unified entity known as spacetime.
Imagine a vast, four-dimensional fabric that makes up the universe. This fabric is spacetime, and it's not just an empty stage, it's an active player in the cosmos. Einstein's general theory of relativity tells us that massive objects like planets and stars create curves in spacetime. These curves are what we experience as gravity.
Picture placing a bowling ball on a trampoline. The ball creates a dip in the trampoline's surface, and if you roll a marble nearby, it will curve towards the bowling ball, eventually spiraling into it. Similarly, massive objects in space warp the fabric of spacetime, creating gravitational fields. These fields influence the motion of objects around them, including light. This warping of spacetime is key to understanding how time travel might be possible, as it suggests that by manipulating gravity, we might also be able to manipulate time. Time travel, therefore, becomes a matter of navigating the contours of this warped spacetime. If we can find ways to traverse these curves, to bend and fold spacetime to our will, then perhaps we can journey through time itself.
Massive objects create distortions in this fabric, and these distortions are what we perceive as gravity. Imagine a spaceship approaching a black hole, an object of immense density and gravity. As the spaceship gets closer to the black hole, the intense gravitational pull would cause time to slow down significantly for the spaceship relative to an observer at a safe distance. Narrator: gravity, the force that keeps our feet on the ground, plays a crucial role in the concept of time travel. According to Einstein's theories, gravity is not just a force but a consequence of the curvature of spacetime.
This phenomenon, known as gravitational time dilation, has been experimentally verified. Atomic clocks placed at different altitudes on Earth, experiencing slightly different gravitational forces, have shown minute but measurable differences in their timekeeping. The more massive the object and the stronger the gravitational field, the more pronounced the time dilation effect becomes. This leads to some mind-boggling possibilities, where time near the event horizon of a black hole could practically stand still relative to our experience here on Earth. Section 5. Wormholes, shortcuts through space and time. Wormholes, also known as Einstein-Rosen bridges, are theoretical tunnels that could connect two distant points in spacetime. Imagine folding a piece of paper in half and then poking a hole through it. The hole creates a shortcut between the two sides of the paper.
Similarly, a wormhole could create a shortcut through the vast expanse of spacetime. While wormholes are predicted by Einstein's equations, their existence remains purely theoretical. Physicists haven't observed any wormholes directly, And creating or stabilizing one would require exotic matter with negative mass-energy density, a concept that's still not fully understood.
If wormholes do exist and we could harness their power, they could potentially allow us to travel vast distances across the universe in a much shorter time than it would take traveling through conventional space-time. This could open up possibilities for interstellar exploration and even time travel itself. However, the challenges of detecting, stabilizing, and traversing wormholes are immense. The scientific community is still grappling with these concepts, making wormhole-based time travel a topic of ongoing research and speculation. Time travel, while exciting, also presents a Pandora's box of paradoxes. A paradox is a self-contradictory situation that challenges our understanding of logic and causality.
Time travel paradoxes explore the mind-boggling consequences of altering the past or future. One of the most famous time travel paradoxes is the grandfather paradox. Imagine a scenario where you travel back in time and meet your grandfather before he met your grandmother.
What would happen if you were to prevent their meeting? Would you cease to exist? If you never existed, how could you have traveled back in time to prevent the meeting in the first place? These paradoxes highlight the potential contradictions that arise when we tamper with the timeline.
They force us to confront the fundamental questions of cause and effect, free will, and the very nature of time itself. While these paradoxes present intriguing intellectual puzzles, they also underscore the potential dangers and complexities of time travel.
The grandfather paradox is a classic thought experiment in time travel that raises questions about the consistency of timelines.
If you could go back in time and prevent your grandfather from meeting your grandmother, would you prevent your own birth? And if you were never born, how could you have gone back in time to change things?
This paradox highlights the potential for contradictions and inconsistencies when considering time travel to the past. It suggests that changing the past, even in a seemingly insignificant way, could have ripple effects that alter the present and future in unpredictable ways.
Some physicists propose the Novikov self-consistency principle as a possible solution to the grandfather paradox. This principle suggests that if time travel is possible, the laws of physics would somehow conspire to prevent any actions that could alter the past.
In other words, if you traveled back to meet your grandfather, something would always prevent you from interfering with his meeting your grandmother, preserving the consistency of the timeline. Perhaps you'd miss your train or spill coffee on yourself at a crucial moment. The possibility of time travel raises profound ethical questions.
If we could journey through time, what responsibilities would come with such power? The ability to alter the past or influence the future carries immense weight, and the potential for unintended consequences is enormous.
Imagine the ethical dilemmas of traveling to the past. Should we interfere in historical events, even if our intentions are good? Could our actions have unforeseen and potentially disastrous consequences on the timeline?
Who would be the custodians of time, responsible for ensuring that time travel is used ethically and responsibly? Similarly, traveling to the future presents its own set of ethical considerations.
Would we be altering the course of natural events by glimpsing the future? Could knowledge of future events rob us of our free will or create self-fulfilling prophecies? The ethical implications of time travel are complex and multifaceted, requiring careful consideration of the potential benefits and risks. As we continue to explore the possibilities of time travel, these ethical questions will undoubtedly remain at the forefront of our exploration. Time travel, once relegated to the realm of science fiction, has emerged as a tantalizing possibility within the realm of theoretical physics.
Einstein's groundbreaking theories of relativity provided the foundation for understanding time as a flexible dimension intertwined with space.
While the practical challenges of building a time machine remain immense, the concepts of space-time curvature, wormholes, and time dilation continue to fuel scientific inquiry and spark our imaginations.
The quest to unlock the secrets of time travel is a testament to our innate curiosity and our desire to push the boundaries of human knowledge.
As we continue to explore the cosmos and unravel the mysteries of the universe, the allure of time travel will undoubtedly persist. It represents the ultimate journey, a voyage through the very fabric of reality. Whether time travel remains a theoretical concept or becomes a tangible reality, it will forever captivate our imaginations, reminding us of the vast possibilities that lie at the intersection of science and imagination.